Before we had modern technology, it became quite difficult to work with a binomial distribution once you had an awful lot of values. So this technique was developed that means that provided you've got quite a lot of values, that means over 50, then we can change from using a binomial into a normal distribution. And the reason for this is if you plot the outcomes from a normal binomial distribution, so totals on 2 dice or something, you end up with a stepped bar chart. Once you've got lots and lots of these possible values, so more than 50, then the curve becomes so smooth that it actually represents the normal distribution, and that's why we can make this change between the two things. And the key things we need to remember is that the mean is always the number of our sample times the probability, and the variation is that times 1 minus the probability. So we're going to be using these formulae in the next section. So here we've got a binomial model because it's been tossed 100 times with a probability of 0.53. Because we've got 100 outcomes happening, it might make more sense to go for a normal approximation, which we can write. So we use the formula mu equals np. So that's 100 multiplied by 0.53, which is 53. And variation is np1 minus p. So 100 times 0.53 times 0.47, which is 24.91. So our equivalent normal distribution has a mean of 53 and a variance of 24.91. Now we can see how similar these two things are because we've got calculators that can deal with it. So if we took, say, the probability that x is less than 6, no, 6 is quite small, isn't it? 36, let's see what probability the calculator comes up with. So we're in binomial. X is 36 out of 100 trials, 0.53, and the calculator, because it's modern technology, can deal with this. It gives me 4.6 times 10 to the negative 3. What happens if I do a similar calculation but with this normal approximation? Then let's see what happens. So menu 7, normal approximation, from negative 1000 up to 36. I want the square root of that, 24.91 and 53. And the normal distribution tells me it's 3.29 times 10 to the minus 4. So similar values but not perfect. Now there's another reason why it's not perfect, and we'll look at that next. So, because we have this difference between a discrete distribution in the case of the binomial and a continuous distribution in the case of the normal, we have to make some careful considerations. So, if in the binomial we want to be strictly less than 5, that means we don't want to use the 5 at all, then we go for less than or equal to 4.5. This is the same as less than or equal to 4. But there's this difference between 4 and 5 in our binomial that the normal, because it's continuous, wants to take account of. So instead of just cutting it off here, we actually go for the midpoint value of 4.5. So when we do our normal approximation, we'll use 4.5 rather than 4. Obviously 5 to 5.5, that's the same thing. If we've got a greater than, if it's strictly greater than, then that's the same as x is greater than or equal to 6, which is the same as 1 minus less than or equal to 5. And we know that less than or equal to 5 is the same as the normal less than 5.5. So 1 minus less than 5.5 is the same in normal terms as greater than 5.5. So being strictly greater than 5, which is 6 and above, we actually, because we've got this difference between where 5 is and where 6 is, we take this midpoint value of 5.5. Greater than or equal to 5, that's the same as 1 minus less than or equal to 4, which is then going to be the same as 1 minus the normal being less than 4.5. This seems an awful lot of numbers to remember. The key thing to remember is if in the binomial it's less than or equal to a, then in the normal it's less than a plus 0.5. And you can always do the conversions that way. So that's the key thing you've got to remember. So if we go back to our previous example where we were looking at 36, when we did our normal, we really should have done less than 36.5. Let's see what difference that makes. I think I might have read that wrong. Let's have a look. 7 binomial. Yes, it was. It's to the minus 4. It's my mistake. So now with this continuity correction, our approximation is much better than it used to be. So here's our normal. We're going to change it into our binomial. So we're going to approximate it to the normal. So mu is n times p, which is 72. And variation is that times 1 minus 0.48, so 0.52. If this is for our binomial, then our normal approximation must be less than 70.5. We use this trick that we add 0.5. And our calculator says that the normal from negative 1,000 to 70.5 with a standard deviation squared of 37.44 and a mean of 72 is 0.403. We could compare that with what happens with the actual binomial. 7 binomial. We wanted 70 off 150 with a probability of 0.48. 0.4036, so pretty close. So a good approximation in this case. Less than or equal to 80, strictly less than 90. So So that's x is less than or equal to 89, subtract x is less than or equal to 80. So in binomial terms, in normal terms, that's y less than 89.5 minus y less than 80.5, which is the same as y being between 80.5 and 89.5. So normal, we're going from 80.5 up to 89.5. Sigma and mu are the same, is 0.0803. So, same thing but in a word question. So, by binomial, we've got 80 bulbs and 55% produce yellow flowers. Find the percentage error when finding 50 flowers. So according to the binomial on the calculator, if there are exactly 50 flowers, we want binomial PD this time, 50 flowers out of 80, if the probability is 0.55, is now the normal approximation, the mean is the mean times the probability, and the variance is that multiplied by 1 minus the probability. Now, x equaling 50 is the same as doing less than or equal to 50 minus less than or equal to 49. So if we swap to our normal, that's y is less than 50.5 minus y less than 49.5 with our rule that we just add on 0.5, and that's the same as y being between 49.5 and 50.5. Now our calculator, so from 49.5 to 50.5 with a mu of the square root of 19.8 and a mean of 44 is 0.03618. So very similar. Percentage error is our binomial minus the normal over the binomial. So the binomial minus our approximation over the what's accurate, and binomial's the accurate one. 100 gives me a percentage 0.915% error. So a less than 1%, which is pretty good for most things.